Welcome, AP Physics, Electricity, and Magnetism students. Today we're going to do our second review lesson on distributed charge. So in the first unit that we studied or reviewed, we were reviewing point charges where we were dealing with little nuggets of charge, real small, maybe down to a proton or a single electron. And we figured out the forces between those objects, the electric fields between those objects, or caused by those objects, the electrical potential energy, and then also the electric potential. So those are the four big ideas that of electrostatics, but they were all about point charges. What we're going to be doing in this review lesson is now looking at charged objects where the charge is spread out and they are so they cannot be viewed as simple point charges. So the four shapes we'll be studying today are the charged arc, where you take a part of a circle or maybe a whole circle, but you cut off a piece of that and the charge now is spread around that arc, and we want to find the electric field at a given point right at the center of that arc's curvature. We're also going to look at the charged ring. Now we've got a complete circle of charge, and we want to find the electric field along the axis that passes right through the center of the ring. We're also going to want to find the electric field of a charged bar, a straight bar, as opposed to this one, which is a curved bar, an arc, and then also the electric field caused by a charged disk. So remember, four ideas of electrostatics. And so I just mentioned electric field of these arrangements, but we're also going to be finding the potential or the voltage of these charge distributions. So we're focused today on those two ideas, not energy and not force, but electric field and voltage or potential. So and also I want to give you a heads up that this is going to be some of the more intense material that we're going to be reviewing, more intense part of the course. What I mean by intense is you have to visualize a lot in 3 dimensions. You also have to be able to set up integrals and perform integrals that are not trivial. So we'll see that. So just a heads up, you probably remember when we studied this, this is on the more intense side in terms of the concepts and procedures of the course. All right, so that was the outline. Again, you didn't have to copy that down because it's what's coming here in the notes here. So here we are, review lesson 2, distributed charge, and we're focusing first on the charge arc. The arc has a charge of Q, and it has some angle that it goes through, and that's theta with a subscript T for like theta total. Maybe you could write out total if you think you might not remember. And then a certain radius. So the theta is like this relative to this point. Like if you took a protractor here and you measured that angle, well, it looks a little less than 90 degrees or pi over 2. So it might be like pi over 2.1 or something. But here's the idea. So we can't use kq over r squared. We can only use that for point charges. So what we do is we pretend that this ring this arc is actually made of a bunch of little point charges. If we snip these into little pieces in our mind, then we can see that this little piece right here with a charge of dq creates an electric field pointing away from that charge if this charge is positive. This here, at the origin, there's an electric field caused by this piece pointing directly away from it. And these vectors have a magnitude of kq over r squared. We can use that formula because we're cutting this into a tiny nugget so that it behaves like a proton or an electron depending on whether the charge is positive. Obviously in this case I picked a positive arc, creating electric fields pointing away from these points, and then here's one pointing away. kq over r squared for all those points. So we can figure out what the lengths of all those arrows are with some math procedures, but we want to find the total. So what we have to do is integrate or add up all the little DEs, all the little pieces of electric field caused by the pieces of the charge. So as we're adding up, we're integrating, you can see from this diagram that the y components of these electric fields are going to cancel because this pink arrow and this blue arrow have the same up and down components if I made a little triangle out of these vectors. The only parts that survive are the horizontal components. So I know that, and then now I redraw this problem here. I'm going to conceptualize in the following manner. I'm going to say, I'm going to pick some arbitrary charge dq, a little slicer here, a radius capital R away. It makes a little bit of an electric field, and this is how I express the idea mathematically that it's only the x component, the horizontal, that survives after the integration. So I put dE, that's the hypotenuse here, times the cos of that angle gives me the horizontal x component that survives integration. So then, what I next have to do now is now find the electric field. Well, let me go down here. Okay, yeah, that looks good. So I'll find the electric field caused by that piece by expanding what dE is. And dE, I use kq over r squared. So k, all this is q over r squared times cos theta. So this expression is this one expanded out, integrated, so I get the total x component of that electric field. So how did I get that dq, the charge in here? Well, this is lambda. The charge, this fraction right here, the charge per length, coulombs per meter. This is a generalization of the formula for the circumference of a circle. Circumference of a circle is 2 pi r. That's the whole angle around an entire circle, theta 2 pi, times the radius gives me the circumference of a circle. Well, if I plug in any other angle for some part of a circle, I get the length of that arc. So this is 2 pi r, but generalized for any angle. So this is coulombs per meter down here. Then I multiply by the meters of this piece, which is r d theta. This is from rotation. You take the radians and multiply by the meters, you get the arc length. So this is kq over r squared times cos theta to pick the horizontal component, integrated from the limits of negative theta total over 2, because that's negative theta over half the arc this way, to positive theta total over 2, half the arc this way. So I'm integrating from this point to that point. So this, I put an arrow here to show you that this is the main idea here. Remember I said at the beginning that you can't review every single detail for the AP. So you've got to pick the highlights. And if you study this and understand the logic here, you'll be able to reproduce it on the AP. The rest is details. And from here you should be able to maybe integrate forward if you remember your integral procedures. But even if you can't integrate beyond this point, the way these free response problems are set up, most of the credit will be figuring this out. The final answer may be one final point out of 4. So if you can set up this, but you have no idea how to integrate, you could get maybe 3 out of 4 points on this problem. So this is the most important part, not the answer. Okay? Now, that being said, let's just take a look at a little bit more about the logic of this integral. If you look closely at this formula, all of these things are constant. This is 9 times 10 to the 9th, the charge on the total charge on the arc, the radius of the arc, the total theta of the arc, same here and here. The only thing that integrates is what I highlighted, cos theta d theta. Cos theta d theta integrates to sine. And so here are all the constants, and then I plug in the limits, so I do more lines. But again, we're not going to look at the details today, otherwise you're going to get overwhelmed. We're looking at the main ideas. Understand this triangle here, the kq over r squared cos theta, and that you integrate. Okay. The other thing that you have to figure out as part of the curriculum is the voltage at this point right here. What's the voltage, the potential at that point? So the charge is smeared out. We know the potential of a point charge, like a proton or electron, is kq over r squared. So, strictly speaking, technically, you would have to set up an integral like this. The total voltage is KQ over R, not KQ, but voltage is KQ over R, the voltage of a proton or a part of the ring integrated over the arc. You could do that and integrate, but it's not necessary, because if you look back at this picture, voltage being a scalar, if you add KQ over R plus KQ over R plus KQ over R for all the pieces here, all of these terms in this integral are constant. So really all you need to do to write the voltage of an arc like this is KQ over R. Again, technically you perform an integral to get that, but if you know this and you put they say what's the voltage or the potential of an arc, and you just write that as an answer, you'll probably get full credit. Okay, so again, that's what we're going to focus on today, because we're looking at the main ideas. So that's the charged arc. Okay, the next charge distribution that we study is the charged ring. So this is like maybe a bicycle tire. Okay, that's actually what I used in class, the bicycle tire. And if you rub the rubber tire with fur, you might accumulate a charge on that rubber tire. So we want to find the electric field along the axis, some distance x from the center of the arc, of the tire or the ring. So again, we have to, we can't use KQ over R squared for the entire ring, but if we split the ring into tiny little pieces and make each part of the ring small enough so it behaves like a single proton or electron, we can then say that the electric field caused by this little piece right here, pointing away if the ring is positive, again I chose a positive ring, that is KQ over R squared, because this is small enough for that formula to be valid. Once again, we realize that we need the total electric field, not just of that piece, but the entire ring. So we're going to add up all the DEs going all the way around the ring. And in other words, what we're doing mathematically is we're integrating again. And when we think of that process in our mind, we would realize that there's a point down here that creates a DE going up like this, with the same Y component as this piece down, that piece up, electric field. So once again we realize that the Y components cancel. The only part of the electric field that survives integration is the X component. And that X component is this DE hypotenuse times the cosine of that angle, cos theta. So then to find the total electric field, I'm going to integrate around the ring. I'm going to talk about the limits in a bit, but again, this is the main idea here, how to set this up. This, in these brackets, is dE, KQ over R squared. This is the cos theta of the previous line. Let's look at the details. KQ, all in the parentheses here. This term, Q over 2 pi R, is the coulombs per meter. Coulombs divided by the meters of the entire ring gives me the lambda, the coulombs per meter. And then I multiply by ds, the length of this little segment here of the ring or tire or whatever I call it. So this is coulombs per meter times meter gives me the coulombs of that little piece right there. Now, KQ over R squared. R is right here, little r. How far away is this point from the charge that we're investigating at this point? This, from the Pythagorean theorem, this squared is that squared plus that squared. So that's where the x squared plus r squared. So KQ over R squared. Now, in the second brackets here, the cosine of this angle is, we could find it in terms of the variables of the other expression by realizing that these two thetas are the same. And so cos theta is, for this right triangle, the adjacent side over the hypotenuse. Adjacent side is x. Hypotenuse is the square root of R squared plus x squared. So I put it to 1/2, but that's the square root. So there, that's the setup. And then we look at this and we say, well, what are we integrating with respect to? We're integrating around the ring, the arc length. And all these other variables are all constants. X, R, no matter what part of the ring we're at in our integration. So all these variables, except for the highlighted ds, come out of our integral. So I collected them all here, and then ds becomes s. The easiest integral you can make is just ds integrated to s. So what is the arc length? What are the limits? It goes from 0 to all the way around the circle 2 pi r. So again, I'm not finishing up the details. Again, this is the big idea that you have to study, the setup, which will be most of the credit anyways. Understand this line where every kq over r squared and cos theta integrated around the ring. Okay, so we also the curriculum has us finding the voltage or potential of the charged ring. And so once again, we know the voltage of a point charge like a proton or electron is kq over r. And it's a scalar, meaning it has no direction. So there's no arrow to it. So technically, when we spread the charge out like that, we've got to add up the kq over r of the entire, all around the ring, okay? However, this is yet another example where we realize, since, you go back to the diagram here, all the charge is at the same radius and away from this ring, and the fact that there's no direction, we could just write the answer as kq over r. This is the r of how far away the points are from our ring. Let me go down again, sorry for all the motion. But it's right here. From the Pythagorean theorem, square root of this squared plus that squared. That's what you plug into kq over r. And if you just write that as an answer, chances are you'll get full credit on the AP. So you don't have to perform that integral to get full credit. Okay, the next charge distribution that we studied is the charge bar. This turns out to, I would say, be the hardest charge distribution that we studied in this distributed charge unit. So we got a straight bar, a length of capital L, okay, and actually I forgot to write some details in here. If this is x equals 0, this is x equals plus L over 2, and this is x equals negative L over 2, okay? Half the bar forward, half the bar backwards from the origin here, because the bar is the whole length L. And we want to find the electric field at the midpoint. That's not necessary. Sometimes they want you to find it here. So, but again, we can't review everything. I'm going to review just the most likely things to be on the AP. Okay, so once again, we can use kq over r squared as long as we cut this bar up in our minds into little pieces that behave like single protons or electrons. So right here, this dq is a length dx, and it creates an electric field pointing directly away from it. And ultimately, we're going to have to add up all the electric fields of all the pieces of this bar. And so that means that at some point in our integral, we're going to be adding the contributions to the piece over here, which creates an electric field up at an angle like this. So once again, the x components cancel. We got a rightward component here and a leftward component here caused by this arrow here. So only thing that survives is the upward or the y component. So we can express that mathematically, that the y component, the dE of this in the y direction, dEy, is the dE, the hypotenuse, times the cosine of the angle. That's going to give me that piece going up that way. Then to find the total electric field, I've got to add up all these dEy's. That gives me the total Ey pointing straight up like that. So this first term in the brackets is dE. Again, kq over r squared. How do we get those details? Well, this is lambda, the charge over length. Total charge over the total length gives me the lambda of the bar right there. Okay? And then if I multiply by the dx right here, then I get coulombs per meter times meters gives me the coulombs of this little piece right there. Okay? And then kq over r squared. So the r is right here. which we can find from the Pythagorean theorem. R squared is x squared plus d squared, so that's where that comes from. KQ over R squared, that's DE right here. This second term is the cosine theta. So here, if we use this triangle right here, this right triangle, cos theta is defined as the adjacent side over the hypotenuse. Adjacent side D over hypotenuse square root of x squared plus d squared. I put to the 1/2. So I put a few more details on this one. I combine all the constants here. Hopefully I didn't forget anything. K, Q, D, yep, we got those there. And then L on the bottom. What's left is the dx on the top, and then these two combined to the 3/2 power. This is one of those integrals, that it is that integral. Remember I said that you cannot solve with a u substitution. You have to just memorize it. I recommend memorizing it, and that then gives us this answer. X over to the 1/2 with a d squared there. And the limit's L over 2, negative L over 2 to positive L over 2. Again, I'm not going to look at the details, so that's it. You got to plug everything in and then simplify the formula. But once again, the main idea is right here, okay? If you can set that up and you don't remember this integral, say, oh, I'm never going to remember it. That's fine. Just get to the here, okay? And you'll get most credit on this problem. And again, if you get 3 out of 4 points on this very hard problem, then you got a good chance of very good chance of getting 5 out of 5, because this is as hard as it gets. You'll probably do even better on the other parts of the exam. Okay, so that's the straight bar. I looked, and finding the potential of the charged straight bar is not in the curriculum. Again, we've seen them throw in things that aren't in the curriculum in the past. But again, we can't try and anticipate everything. Since it's not in the curriculum, we're going to skip finding the voltage of this straight bar. Okay, the final geometry for today is the charged disk. Okay, so what I mean by that is, let's suppose you have like a disk that's completely solid, like I guess a dinner plate or something like that, with no holes in it, and it's a flat dinner plate. Maybe a pizza is a better example. And you spread charge evenly over the entire pizza. And so through the center, out to the edges, charge all the way around, evenly spread out. So we're going to find the electric field and the voltage. Now let me just say, it turns out the electric field, finding the electric field of this arrangement is not in the curriculum, but the voltage is. So I don't quite understand. So I'm going to include the electric field in this review lesson just to be on the safe side, because, you know, it does ask about the voltage of the charged disk. All right, so I'm going to recycle the formula from the last part of last geometry, the electric field caused by a ring. I didn't solve it completely out, but if you did, you'd get something like this. KQX over x squared plus r squared of the ring. This is, the ring, by the way, is the total radius is r, but this piece is only r right there. So that's the electric field pointing directly away along the axis. So I'm going to find the electric field of that piece using that formula, and then I'm going to add up all the pieces of all the rings. In other words, I'm going to integrate for radius 0 to capital R. Now, in order to do that, I've got to expand out what the charge of that ring is. So if I cut this ring out and this disc were made of putty, I could open it up and create a rectangle out of it. So I cut it like this, and I just bend it open and create a straighten it out. And so I could say that the charge in that little ring is sigma, the coulombs per meter squared, times the meters squared, the area of this ring. So coulombs per area times the area gives me the coulombs of just that piece. So the sigma is total charge over total area of that disk, Q over pi r squared. And the dA is the area of this rectangle, which is length, the circumference here, length times width, length times width, okay? So this whole thing is the charge in that ring. So I use this formula now, and I say that the total electric field will be the electric fields of each of the rings integrated over the entire disk. In other words, from 0 to R, This is the K, the Q that I worked out over here, times the X, right? So I'm using this formula over this denominator here. And this actually, I highlighted the parts that integrate. All these other terms are constants, so they could come out of the integral. Oh, and the X also. So we have r d theta times this to the negative 3/2. And if you use a u substitution of x squared plus r squared, you can integrate this directly out without memorizing the answer. You can do it with u substitutions. So it is totally doable, totally within your calculus skills. And then you just, again, I don't show you the details, but that's the answer. Okay, here's the part that's actually listed as in the curriculum, the voltage of the disk. Okay, so what I'm going to do is say that the voltage is K, Q over R. Remember, that's the voltage of a point charge. Okay, but remember that I could use KQ over R for the ring, which I had in the previous two of our notes. So I'm just going to use K, the Q in this ring, divided by the R, which is the R along this diagonal here. How far away this point is from the charge. So that's, let's see, maybe I'll go like this. K, this is the Q, which is all right here. Okay, so there's the Q, which I plug in there. K, Q over R. Okay, R being again that distance from the Pythagorean theorem. Square root of x squared plus little r squared. Okay, so now I highlighted again the parts of the formula that are relevant to the integration. All these other terms are constants. They could come out of the integral. Again, you could do the same u substitution, this to the negative 1/2, and then this would be like kind of getting your du, and you could integrate that with techniques that you know and understand from the calculus. So that's it, distributed charge. Okay, again, very heavy. Go back and just study these, you know, focus on these where I put the lines in. Okay, so right here, how to set up this integral, how to set up this integral for the bar, okay, how to set up this integral right here for the charged ring like a tire, okay, this line right here, and then finally how to set up for the arc. This line is what you want to study. Okay, so again, the charged arc, the charged ring, the charged bar, and the charged disk. All right, that's it for today, and I'll see you in review lesson 3.